This video is part of a course on food physics, of which this is the theory section. This one discusses heat transfer when there is phase change involved. And the one before this discussed transport processes that includes heat transfer without a change of phase. Now, the immediate follow-up module after this one has change of phase. It discusses change of phase in multi-phase porous media context. The difference between that and this one is that in this module we consider phase change at a single temperature, as opposed to in the other module where phase change would be over a temperature range. Looking at the big picture of many ways to describe a food process mechanistically. So from less to more mechanistic this way, we can have many choices from the most simple to the most complex, and we are here. So the model we are going to describe here, the way we are going to describe the physics, it's less complex and less comprehensive than, let's say, a multi-phase porous media model that has distributed evaporation or distributed phase change. So phase change can occur anywhere inside the material. It is the one we are going to describe here is less sophisticated than that, but it certainly has a lot more physics than, let's say, lumped parameter or let's say single phase equations that do not consider phase change. So this is an important one because it gives reasonable estimates of how long does it take for the phase change to happen for many different scenarios. We will discuss this in three parts. First, the broad idea of what is a sharp interface or sharp boundary formulation. This will be followed by governing equation and boundary conditions of such a formulation, and that will be followed by a drastic simplification of that and how we can get estimates of things like freezing time. What do we mean by sharp boundary phase change? So here's an example of phase change process. In this case, it's freezing of meat, and the freezing progresses from this end. Now you can see where it's frozen or the frozen part ends and the unfrozen part begins. And so the interface between the frozen and the unfrozen is what we are referring to. In the case of sharp boundary formulation, we treat this interface as like a line of zero thickness. It's a very sharp boundary. That's what we mean by sharp boundary. It is an assumption. So let's say for freezing, water in the food material is not pure material, pure water. And so it doesn't freeze at one temperature. And as there's more freezing, the rest of the solution gets concentrated, freezing at even lower temperature. So freezing happens over a temperature range, and therefore it will happen over a finite distance. So this sharp boundary, the one that we are showing here, is really an assumption. Another example, and by the way, the picture is from the literature, and another one again from literature. In this case, it's not freezing, but it's freeze drying. Freeze drying of like a disk, and freeze drying is the material is frozen first, and then the water is allowed to sublimate at a lower pressure. And so this freeze drying, again you can see a drying front, that you can see um, it separates between frozen and dried, and that's the interface that we are talking about. Now you can see that in both cases, the freezing on the left and the freeze drying on the right, before that, the freezing on the right, the freeze drying on the right, you know, here also it doesn't have to be a very sharp one, because the sublimation happens over a small temperature range. It does not have to happen at just one temperature. However, the pictures from the left and the right, you kind of see that it may not be too bad. It may not be terrible to assume a sharp interface. That is indeed the case. That is why we are even talking about this particular formulation, sharp interface formulation, and that's why we have this video. Wonder why we have a separate framework of physics or a separate video when phase change is involved. Why is phase change such a big deal? So to make the point, I have this curve for water enthalpy versus temperature, and you notice of course enthalpy increases with temperature because enthalpy is mCp T minus T reference. So as T increases, enthalpy increases, and that's what you see here. But you notice at the magnitude that even over a fairly large range of temperature, minus 40 to 0, the enthalpy change that is corresponding to this sensible heat is small compared to the latent heat change at 0 degree for pure water going from ice to water. So this latent heat amounts are huge, and they are also released in a very complex manner. This is what makes phase change problems more difficult, and this sharp boundary phase change, sharp interface phase change is just one way of handling such phase change problems. So again, so much heat needs to be removed at this interface that we can make some special consideration for this interface, or we have to make special treatment for the interface. Here we want to have an overview of this framework of sharp interface formulation for phase change. And again, I chose this picture of freezing from the literature here, and I drew a schematic kind of based on that, where you see we have some heat transfer process from the surface that changes phase in this region, and then the other region is where phase change has not happened yet at any particular time. Now this was drawn with the freezing picture in front, but the same idea applies for, let's say, deep frying, where you have heat coming in and evaporating at this interface, and those vapors going out, and again you have a sharp interface, or we can approximate to a sharp interface, to the right of which we have the crust, and to the left of which we have the core with more moisture. Another example would be freeze drying, where the entire material would be frozen. So at any given time, the left of the interface would be still frozen, where the right of the interface would be dry. So all of these very different processes where we have phase change, they can be treated within this framework. So what is the main idea of this framework? How do we develop the equations and then solve it? Basically, the idea is very simple. So we have two zones, one on the right side where the phase change has already happened. So there we use the normal energy equation. So in some case that will just be just the heat conduction equation, but with the properties of this zone. Likewise, for that same problem on the left hand side, then we'll have the same equation but properties of the region without, where phase change has not happened. Or let's say this is freezing, then this region is still unfrozen, so we'll use the properties of unfrozen region. And all we need to do is heat conduction here and heat conduction here. So that part is no different than situations where you do not have phase change. What is different and what makes all the difference is we do not know where this interface is. So we have to find that interface. So for that, we need additional information. And that additional information comes this way. Heat flux from the left, like this one, and to the right, because it's at a point, at a line, they would normally be equal without phase change. But when there is phase change, they will not be equal, and the one from the left and from the right, they will be related to each other by the latent heat that is either given off or absorbed in that interface due to phase change. So this is new, and the amount of this will depend on how fast the interface is moving. Said another way, the rate at which the interface moves can be related to heat flux from the left and heat flux from the right, which individually we know, because in the left, for example, let's say in freezing, we are doing a heat conduction calculation of in the unfrozen media. That's all we need. And then on the right is just a heat conduction in the frozen media. So these two can be found separately, and then they can be related by this equation to the rate at which the interface moves. And the same kind of idea can be applied for frying with more physics details, or freeze drying and so on. So this problem is also called a Stefan problem. It's a very well-known problem in heat transfer literature, existed for many years. And so, but this is the qualitative understanding or the overview of the idea. We keep talking about sharp boundary. It would be nice to contrast this with something that is not a sharp boundary. So what is this other possibility? So here are the two kind of conceptual schematic. On the left is the sharp boundary where the phase change only happens in this interface, whereas on the right is the opposite of sharp boundary, or distributed phase change. So phase change can occur over a region. We can set it to occur anywhere in the region, but if we do the physics right, we will see that it kind of happens over a region, and in some cases that region can be very thin. So again, to contrast then, here to the left for sharp boundary, we solve two equations for two regions and another equation at the interface. In contrast, here we solve just one equation over the entire domain. Now that may sound easy, but that also has its own complications. The examples of this can be seen in the next module on porous media, where we include evaporation, or it can be seen in applications like in freezing. So as we continue relating to and contrasting with distributed phase change, here is another way to look at the differences and the similarities between the two. So back to this enthalpy curve that we talked about, this phase change, let's look at the freezing part, okay? And so in reality, water in food material has other things dissolved in it. So it does not freeze at exactly 0. In fact, it freezes at some lower temperature, and more ice forms, the rest of the water gets more concentrated. So its freezing point is even lower. And so this latent heat, instead of a sharp change like that, it actually looks more like that. So the latent heat is released over a range of temperature. So in other words, I'm making the point that the distributed phase change, so if the latent heat is released over a temperature range, that means spatially also there will be a range, there will be a finite region over which phase change happens and not a sharp interface. So then that comes very much from real world. So the distributed phase change is kind of more normal, but formulation of distributed phase change can get complex, and so this sharp interface phase change is an assumption that can give us a lot of the physics and reasonable estimation of time, but without some of the complications. Another example, the other end of the curve, again for boiling or phase change at the other end of the higher temperature, This also does not have to happen at exactly that one temperature, because when the temperature is high enough in this region and food is like a porous medium, so there is enough empty space for evaporation to happen. So evaporation can happen at temperatures lower than 100. And so, which means again, I'm giving reasons that in reality, the phase change, even for the one from water to vapor, is distributed. But as I said, consideration of this phase change distributed over a temperature requires often more complex formulation or some other detailed experimental data. That's why we look at the sharp interface formulation as a good approximation. So the distributed phase change that happens over a region is more realistic, but this sharp interface can let us analyze the system and look into it with less effort often. Using computational results, we can actually take a little closer look at just how thick or how wide the interface is and how reasonable is the sharp interface assumption. So I'm going to do this using computation for two different processes. So first, it's for freezing. And what I'm contrasting is, to the left, I have computation for pure material, and to the right, I have computation for beef tissue as a representative food material. And the same would be true for other water containing biomaterials. So the left one, in the animation that you're seeing, this is actual calculation based on the formula or the framework that will be developed in this chapter. So this animation shows actual calculation for a sharp interface. And so it's being frozen from here, and the blue part is the frozen, red part is unfrozen, and so the frozen part proceeds inside, as you see. And what you see is a very sharp interface, because that's how the problem was formulated. On the right side, on the other hand, we formulated the problem saying, okay, so the freezing can happen over a temperature range based on other physics that we are not getting into. And let's see just how wide is the region over which phase change happens, because that will tell us whether it's a sharp interface or not. So what you notice are two things. One is that the interface, which is the distance between the two white lines that are moving, so to the left most white line, to the left of the first white line, is all frozen, so all blue. To the right of the second white line is all red or all unfrozen. So the distance between the two white lines is the width of the interface. So the width of interface, you can see, increases with time as freezing happens, and it is definitely not a strict sharp boundary interface. So that is the major contrast with the left figure, where it stays at a sharp interface. So this should tell us what, visually, what we mean by a sharp interface, that's on the left, and distributed evaporation over or distributed phase change, I'm sorry, over a region. That's the right figure. So the thing is, you can see the two pictures are qualitatively similar. Of course, they're both calculating for freezing, but we have these detailed aspect of the interface increasing with time. That is the reality, and that is not captured as well in the left one. But we will see that the left one can give us reasonable estimation because it still considers the latent heat, which is the bulk of the amount of heat that needs to be removed. So here is another look at just how wide is that interface, meaning when can I make the sharp interface assumption and when I cannot. So I pick the example of freeze drying, and again a picture from literature that shows how the drying front here, how it moves over time when drawing some sort of a cylindrical disc. So the question we're trying to see is just how wide is this interface in case of freeze drying. So now to the left, I show you computation of freeze drying. So in this case, so we have a thick material all the way. So this is a boundary where heat is coming from, and this entire material is this is the thickness of the material. So as heat comes in, it vaporizes, and then the vapor leaves, okay? And the diagram below shows the rate of sublimation, okay? So where the phase change is taking place as a function of distance. These calculations were done not assuming sharp interface or sharp boundary. I repeat, the calculations were done assuming sublimation takes place over the entire region. It was formulated that way. But the results that we get show a very interesting story. So at this time, for example, the sublimation happens over this thickness. That's all. So the rate of sublimation is high. That's because initially the rate of heating is high from the boundary, and so but all of that happens over a very small region. Talk about sharp interface. This looks very much like a sharp interface, even though we allowed it to be distributed, to happen over a distance. And then over time, as time goes, you can see it may change ever so slightly, but it is almost like a sharp interface. And so with time, that sharp interface stays. So here is an example that is freeze drying, where sharp interface assumption could be quite reasonable. To summarize this little subsection, we discussed what is the general idea of sharp interface formulation for phase change, and showed examples that the sharp interface formulation can be quite reasonable for some situations at least.